Hello there, welcome to Everything Polar Coordinates Level 4. In this video we're going to be discussing a little bit about dot products and divergence in polar coordinates, and we're going to be using this nabla operator which we derived in the last video. So first let's go ahead and talk a little bit about dot products very generally, and I actually did use dot products a little bit in the last video, but I haven't explicitly talked about them yet. So we've already talked a little bit about how we can think of Euclidean space as a vector space or as a displacement vector space. But one thing we haven't talked about is that we can be a little bit more specific than that. We can define Euclidean space as an inner product space, right? Because we can not only take two vectors v1 and v2 and add them together, or scale up some vector, v1 with some scalar constant alpha, we can also introduce a form of multiplication between two vectors, v1 dot v2, okay? And this very generally is called an inner product for any vector space, although in the context of Euclidean vectors, we refer to this as a dot product. Okay, and this is going to output some scalar value. It's going to output a scalar value. Okay, and if you want to be particularly mathematically rigorous, there are certain postulates that an inner product must satisfy for an inner product space. We could go through those axioms, but it's not particularly helpful, especially, from a utilitarian perspective of, I just want to know what a dot product is to apply it for physics. So that's what we're going to talk about a little bit. So specifically, let's go ahead and say that you give me two vectors. I'll call this vector v1, this vector v2, right? And they have some angle of theta between them. In that case, the dot product v1 dot v2 is simply defined as the magnitude of v1 times the magnitude of v2 times cosine the angle between them. Of course, we can almost immediately appreciate what this definition does physically, right? So let's go ahead and look at v2 cos theta here, right? So we can imagine breaking v2 up, right, into a component that's parallel with v1 and a component that's perpendicular with v1, right? So of course, v2 cos theta is going to be this component here. So let me just go ahead and indicate that this guy here is v2 cos theta. Okay, so we can see that we've taken v2 and we've found its component in the v1 direction, or the projection of v2 onto v1. So that's this first part here, and then we just multiply it by the size of v1. Okay, so that's really the basic definition of a dot product. So ultimately we have this operator that's multiplying the components of vectors that point in the same direction. Now in physics, typically we express, our vectors v1 and v2 in terms of basis vectors, correct? That's kind of what we focused on the second video in this little series. We focused on coming up with, nice basis vectors for polar coordinates r hat and theta hat, right? And we came up with these in terms of x hat, y hat. The point is we define some basis vectors for, our Euclidean plane, or if we're talking about 3D, Euclidean space, right? Now, these basis vectors, it's really important to recognize that we design these to be orthonormal, okay? Orthonormal basis vectors. What does that mean, right? Just as a reminder, or they are one, right? Orthogonal, right? So if you recall, like with r hat and theta hat, if we looked at a point, we said, oh, our r hat vector points out from this point, and then we had our theta hat unit vector, which was perpendicular to r hat. So the orthogonality condition on our basis vectors is very important, right? Because it basically indicates that we have two completely independent directions, right? In 3D space, we have up to 3 orthogonal or independent directions that we can move in. Okay, and then of course the second part of this is that these vectors are normalized. normalized, which means that they have a unit length of 1, right? These are unit vectors. And of course, if you combine the words orthogonal and normalized together, you get out orthonormal basis vectors, right? And the point I'm emphasizing here is that while yes, you can have basis vectors that are not necessarily orthogonal or normalized, right? It's just not very practical to work with those basis vectors in physics. And it's for that reason that we're now going to talk about dot products of specifically orthonormal basis vectors, okay? That's going to be very helpful for us. So consider that we have E1 hat, E2 hat, and E3 hat, a set of up to 3 basis vectors for 3D space. And we define that these are orthonormal basis vectors, right? In that case, what is, like E1 hat dot E2 hat going to be? Well, this is just going to be the magnitude of E1, which is 1, times the magnitude of E2, which is 1, times cosine of the angle between them. Oh wait, they're orthonormal. They have a 90-degree angle between them, so this is cosine 90, or in other words, this gives you 0. Okay, but if I take E1 hat and dot it with itself, E1 hat, now this is going to give me 1 times cosine of 0, which is now 1. Okay, so look, if these indexes are the same, right, or if these indices are the same, then I get out 1. And if these indices are different, I get out 0. So actually, we can introduce a very general definition here that EI hat dot EJ hat is going to be equal to a symbol called the Kronecker delta IJ. Now, the Kronecker delta IJ is very easy. It's simply defined to give out 1 if I is equal to j and 0 if I does not equal j. Okay, so that's how we kind of define this, dot product with index notation. But just make sure that we're clear on what this means. This is saying if I have 2 basis vectors, EI hat and EJ hat, if those vectors happen to be the same basis vector, right, they point in the same direction, it gives me 1. Because they're fully projected, they're already projected onto each other completely, right? And if I have 2 basis vectors that are totally orthogonal to each other, they don't point in the same direction at all. So the projection of one onto the other is just always going to be 0. So this here is a really nice way to summarize the dot product between 2 orthonormal basis vectors, just to make sure that we understand the ideas, right? What would x hat dot x hat be equal to? Well, this would be equal to 1. This is basically the equivalent of saying that we have some EI hat, dotted with another EI hat, right? What about r hat dot theta hat? Of course, these are orthogonal to each other. This is going to give me 0, right? And so on and so forth. And we can use these, very simple definitions to come up with dot products of more complicated vectors, right? For example, if I have 3x hat plus 4y hat dotted with 5y hat, right? We could distribute this out, we'll do it very literally one time. We have 3x hat dot 5y hat plus 4y hat dot 5y hat. But of course, this x hat dot y hat term is going to go to 0, right? The y hat dot y hat is going to go to 1, and 4 times 5, right? We're going to be left with 20. We're going to be left with 20. And again, notice that this 20 is a scalar value. Our dot product, our inner product for this space, took 2 vectors and output a scalar value. That's really important. Alright, so next let me go ahead and talk a little bit about divergence, and this is going to start off sounding totally unrelated to the dot product, but we'll talk about this. So let's go ahead and consider that I have some surface, some closed surface in 3D space. So this is 3D, right? This is like a shell that's, enclosing some volume in 3D space. And let me go ahead and call this surface S. Now, a vector field, remember, it assigns a vector at every point in Euclidean space. So we could go ahead and imagine that at the surface S, we have a bunch of vectors, right? And I'm going to draw them all pointing outward for this example. And what we can do in math is we can define a concept called flux, right? And flux is simply referring to, right? Imagine that you summed up all of the contributions of these vectors kind of pushing out on the surface S, right? Flux is capturing that idea. You sum together the total push in or push out from all of the vectors acting on a surface S. Or maybe these vectors could represent like fluid flow or something, in which case this would indicate the total amount of water like moving in or flowing out of, the surface S, right? Okay, and let me go ahead and call this field that I'm working with F as a function of my position R, okay? And so, it's actually very easy to define flux. All that you really need to do is imagine that you have little infinitesimal patches that this surface is comprised of. Go ahead and call these patches ds, right? And they're actually, we could indicate, the orientation of these patches with a little unit vector n hat. If we take n hat times ds, it gives us a little infinitesimal vector I'm going to call ds. Alright, and keep in mind, just by convention, these ds vectors are always oriented to point outwards. Okay, we just use that by convention. Literally, all that you need to do to come up with flux, let's go ahead and say that, the field at this location points like this, right? Again, what we need to do, we need to find the similarity between these two vectors. This is vector f here, and we have some vector ds here. How do we indicate the similarity between these two vectors? The dot product, right? What we just talked about. If I take f of r dot ds, and now I integrate this, this infinitesimal over this entire surface S, right? Then I'm going to, this is defined as flux. This is defined as the flux through the surface S. All right, so now let me talk about a very related concept called divergence, right? So, of course, we defined our flux here. I went ahead and updated my picture, right? I just specified that we could consider this surface as centered around some point P, right? And, again, emphasizing that this surface is bounding some inner volume V here, okay? Here's the point. First thing I can do, I can take my flux. Let's go ahead and just define some flux per this volume, okay? So now I just divided both sides, by V. Now I have flux per my volume, all right? Now, next thing we're going to do, what happens if I take the limit as V goes to 0, right? In other words, think about what I'm doing. I'm taking my surface S here, and I'm crunching it together. I'm making it smaller and smaller and smaller until I limit down to just an infinitesimal surface, around this point P, okay? So we take that limit as V goes to 0. Then this limit is going to give us, this is defined as the divergence of F at this location P, okay? Okay, and very colloquially, I just went ahead and wrote down that this divergence quantity, it just indicates the inwardness or outwardness of my vector field at, this point P. right? Again, just drawing this parallel that, yeah, this really is just, it's an infinitesimal limit of the notion of flux. It's just indicating that, you know, still kind of this push in or push out of my vector field. It's just in this infinitesimal limit now per some infinitesimal volume, okay? And the way that we calculate out this divergence, okay, and I'm not going to prove this in this video, but it turns out that this is the same thing, right? You have to prove this, that the dot product of the nabla operator with your field f is going to give you the divergence of f. Okay, this is a really important kind of connection to make. And in fact, it's so important that even though you prove this fact, I'm going to call this the definition. Okay, I'm going to say that the divergence of f is defined as the nabla operator dotted with your vector field f. Okay, that's really important. And again, we could evaluate this at a specific point P, or just like any other derivative, we could evaluate it for all points. Okay? Alright, so let's go ahead and use this definition then to calculate what divergence looks like in polar coordinates. So go ahead and consider that, you know, we already found this nabla operator in the last video, and we have some arbitrary vector field here, right? Written in terms of some, you know, r component, which I'm calling f of r. This is some function of, you know, your coordinates r and theta, right? And it points in the r hat direction, plus some, you know, theta component of your vector field here, right? So this is just an arbitrary expression for a vector field. We're going to go ahead and we're going to figure out what the divergence or grad dot f is, okay? So let's go ahead and calculate this out. So what we have to do, we just have to take d dr r hat plus 1 over r d d theta theta hat, and we dot it with my arbitrary vector field fr r hat plus f theta theta hat. Alright, and the most important thing for me to emphasize here, just remember to apply your derivatives first and then take the dot products, okay? Because when you're applying your gradient operator, you need to keep that information of, you know, derivatives of these little unit vectors here also before taking that dot product. So I'll show you what I mean. So let's go ahead and look here. Let's look at these first two terms, okay? This is going to give me r hat dot, I apply the derivative first, d dr of fr r hat. Okay, that's my first term. All right, and now from here we can just start going and getting more terms. So 1 over r theta hat dot d by d theta fr r hat. Right? Next, r hat dot d dr of f of theta theta hat plus 1 over r theta hat d by d theta of f theta theta hat. And you can see now that we're going to have to use the multivariable product rule, right? We're just going to have to product rule each one of these guys out. Alright, and now expanding things out with the product rule, we get up to 8 terms here, but of course we can see that a lot of these terms are going to end up going to 0. And really, these derivatives with the unit vectors, we've already done some practice with that in the last video. Okay, so, you know, at this point we know that we just write our unit vector in terms of Cartesian coordinates, right? And then we can use that, you know, in order to find the derivative of each of our unit vectors, right? So, for example, this first term, we know it's just going to immediately go to 0. Just common sense, we know that the r hat just has a cos theta x hat plus sine theta y hat term. There's no r appearing anywhere in there. So in fact, you know, same deal with theta hat. I can immediately see this is going to go to 0, right? The other thing that I'm going to start doing, I'm going to start ignoring terms that I can immediately see are going to dot product to 0. So for example, this r hat term dotted with this theta hat term, yeah, I know r hat dot theta hat is going to dot to 0 based on what we talked about earlier. So this guy here is unimportant. What else? What else? Oh, this guy here, unimportant there. Okay, we're down to just 4 terms now. Okay. I know that dr hat, d theta, is ultimately going to produce something in the theta hat direction. Okay, so I know for a fact this is going to output something with a theta hat term in it. So this guy here is actually going to be useful because theta hat, oh, let me put this dot back in here, there we go. That this theta hat dotted with this theta hat, that's going to give me something important. This guy, on the other hand, d theta hat, d theta, this is going to give me something useless. This is going to give me something in terms of r hat. This guy is just useless here. So really we're down to 3 terms. Okay, let's go ahead and explicitly calculate out what dr hat d theta is. Okay, just for a little bit more practice. So I know that r hat is equal to cos theta x hat plus sine theta y hat, and therefore dr hat d theta is going to be equal to minus sine theta x hat plus cos theta y hat. Oh, okay, or in other words, this is just exactly theta hat. Okay, perfect. I knew that it would have something to do with theta hat. Now we can see it's precisely theta hat. Okay, great. So now, let's just go ahead and expand this dot product out. So I'm going to have r hat dot r hat, what's that? Just 1, right? So dfr dr plus, okay, let's go ahead and expand this out. Theta hat dot theta hat, what's that? Okay, just 1 again, nice. So we have 1 over r times fr. And finally, let's go ahead and expand this guy out. We're just going to have, what's theta hat dot theta hat? Okay, just 1 again. 1 over r df theta d theta. Cool. Right, I can go ahead and just reorganize my terms down here. I can call this 1 over r d of the product of r fr dr, and then plus 1 over r df theta d theta. Okay, and there we go. This is now, right, we have now derived an expression for the divergence of some arbitrary vector field in polar coordinates. Okay, and there we go. Alright, I'm going to go ahead and end this video here. If you enjoyed this video, consider subscribing to the channel, and let me know in the comments. I love to hear about people getting on board. But other than that, thank you so much for watching.